Okay, good morning. So the purpose of today's lecture is to tell you about D-branes. So in the last lecture, we discussed objects in string theory that are charged with respect to Raman gauge field. And these are black D-branes. So these are so p spatial and time, one time direction, and from there emanate both metric and unsymmetric tensor gauge field strengths, and there are p plus 2 forms. So that if you write it as curvature of p plus 1 form, this p plus 1 form naturally coupled to the world volume sigma, which is p plus 1 dimension, like that. Okay, and I guess this should have been stirred in order for this to be electrically charged object. Okay. And so we wrote down some explicit solution to Einstein equation coupled to dilaton and this unsymmetric tensor field, which carries both tension, so therefore curves the space, and also charge like this, which is responsible for this electric charge. Okay. But because you have self-duality, the duality symmetry in type 2 string theory, which maps p plus 2 form into a 10, so 8 minus p form. So that means that just like in Maxwell theory, where you can consider both electric and magnetic charges, well, you can consider that the magnetic monopole has not been discovered, but if you postulate the magnetic monopole exists, then as Dirac showed, electric charge should be quantized. So this was actually motivation of Dirac to consider magnetic charge. So if you assume that if you have gauge theory, and if you assume there are objects in the theory which are both electrically and magnetically charged, then all these charges are quantized. So that means that these charges are quantized. And so if you have any unit of charge, then there is an extremal condition that we derive. So it's bounded like that. So this is the bound for the absence. So the absence of naked singularity was like that, and the equal, the black p-brane saturating this inequality are called the extrema. So what I meant by charge quantization is that this m takes integer value, and this is required by assuming that there are objects both electrically and magnetically charged with respect to this. So, but this is interesting. So that means that there is some kind of granularity to the black p-branes, and so when n is large, m is large, so the curvature near the horizon of this black p-brane is small, and if n is sufficiently large, the curvature is much smaller than the Planck scale. So therefore, this type of description in terms of low energy effective theory, solving Einstein equations, is justified. But when n becomes small, this becomes small, and in the extremal limit, the mass is small, the curvature near the horizon is large. And in particular, if you take extremal limit, except for the case of p equals 3, there are naked singularity on the horizon. So the low energy effective theory breaks down anyway. So you need some alternative description when either p is not 3 or n is small integers. And so there is actually an alternative description. And so these are D-branes. Okay, description in terms of D-branes supposed to be valid for all n, but for small n it's particularly simple because you can use some perturbative description. But it's believed that for any n, this is a good enough description. So there are some overlap between these two regions, and that observation gives rise to various interesting phenomena such as ADS-CFT correspondence that we'll discuss later. So let's introduce the notion of D-branes. So D-branes, to consider D-brane, we consider similar things to begin with. You consider some kind of object of p spatial dimension and one time. We may also consider D-brane spread in the spatial direction only. So, but for now, let's consider this kind of configuration. So instead of, so when n is small, away from these D-branes, the space is expected to be flat. And for when n is small, then you would expect something funny happens only in the neighborhood of this subspace. So in order to model it, so what was proposed was consider the following things. So in the bulk, away from this D-brane, you can have closed string. But on the D-brane, this string can open up and end on the brane. So you can do those kind of things. So that namely that we are allowing the string end here. Okay? So if you consider an end point on the string, which means that on the worksheet, we'll be considering boundary. So if you have a closed string propagating over here, the statement that it can end here means that you can have a boundary. So I don't have a color chalk, so I guess I have to just draw in this way. But so string propagating in this direction, but it can branch out and end over here. Okay? So that namely that there are boundaries on the worksheet. So in order to understand D-brane, we first have to consider the boundary condition on string worksheet. So there is a famous joke about academic spouses you might have heard about. So you go to a party. If you have a research theoretical physicists, for example, mathematicians, you go to a party and sometimes you take your partner to the party, and your partner may not be in the same field, and so when you go to a party where most of the participants are mathematicians, theoretical physicists. Sometimes it's difficult to find a common topic to discuss about. And but there is actually one thing that the partner can always say, which is always a good thing to say, which is the following. So suppose you take your partner to the party, and then there are some highly technical discussion mathematicians and theorists are talking about. So you get somehow in an awkward situation where you don't know what to say. There's always one thing you can say that is always good, which is what happened to the boundary. So when you say that, almost always everybody says, "Oh, that's a very good idea. I haven't thought about it." And then you can continue the conversation. So what happens when the worksheet has a boundary? Okay, so let's consider the situation where boundary is extended in time. So namely, what I mean is that so suppose you have the worksheet. So suppose you have some worksheet like that, and then you have a boundary here. Okay, so you have a boundary here, And so you want to know what kind of boundary condition we should impose. So let's start with a simple action. We'll modify that later. So this is sigma. I use sigma for the D-brane world volume, but this is two-dimensional worldsheet of string. And so the action is d square z 4 pi alpha prime del a x mu del a x mu, excuse me. So let's first consider the simplest case when you have a flat Minkowski space and no B field or nothing else, just this simple action. So one thing you want to do is to find a consistent boundary condition. So you vary the action. So you vary the action, so that means that you take variation of the action of this thing. But then you realize that, there are two terms that you can add, because you can write this as del x mu, del a x mu, minus del alpha del x mu, what am I doing? Minus del x mu, del a x mu. Okay, so you can write variation of this into two terms, just like you do in undergraduate classical mechanics. And then, of course, the stationary condition of the action with respect to the variation in x inside of this worldsheet imposes the equation motion, that this should be equal to 0. Normally, we drop this term because it's a boundary. Normally, we drop this term because it's a boundary. But if you have a boundary on the worldsheet, we cannot ignore that. And so this, if you impose the equation motion in the bulk, this in addition gives rise to a term like this. So this is a total divergence. So this is equal to del x mu, del a x mu. Okay, so if you impose the equation motion del a x is equal to 0 in the bulk of the worldsheet, then on the boundary we get this condition. So you have a choice to make. So you want this to be 0. So you have two choices. So on del sigma, you have two choices. You have del mu, del a, x mu, dza to be equal to 0. So that means that either del x mu is equal to 0, or del x mu did I make a mistake? Yes. I think it should have been b, and then you have to have epsilon ab by the Stokes theorem. So the equation I should have satisfied is this, where this symbol means that this is a direction perpendicular to the boundary. So this is a Dirichlet condition, and this is Neumann condition. So you either satisfy Dirichlet condition, which means that if you have a boundary, the value of x is fixed, or if you take derivative in the direction perpendicular to the boundary, it stays flat. So you have two types of boundary conditions. So this is geometrically clear what these boundary conditions should mean. So for example, suppose the D-brane is just one-dimensional object extended in time. So in that case, so D-brane is located at fixed point in space. So for all the spatial component, you should satisfy Dirichlet conditions. Whereas in the time direction, D-brane can be located anywhere in time. So that means that when string ends on it, it can fluctuate in time direction. But in order for the boundary condition to be consistent, the boundary behavior of string for the time behavior of the time coordinate of the string should satisfy Neumann condition. That's what this means. Okay, so I hope this is clear. So namely that the consistency of the boundary condition in this very most simple setup, it should be that it should be either Dirichlet or Neumann. And so in particular, if you have Dirichlet condition, then that determines the location, the corresponding coordinate. So if certain direction in string coordinate satisfy Dirichlet condition, that determines the location of this object. So D is actually Dirichlet. So the location of D-branes is determined by the string coordinate satisfying the Dirichlet boundary condition. Okay? Before I go on, maybe it's useful to just mention some possible generalization. We'll discuss more sort of extensive generalization later, and I hope that we can get to discussion of D-brane in Calabi-Yau manifold too, and the interesting behavior of them under mirror symmetry. So I hope we will get there. But let me just briefly mention some generalization. So suppose instead we consider this action. So here I'm considering that the space-time to be flat Minkowski space, but one could also consider introducing metric. Let me just, let me write it this way, and also introducing some unsymmetric tensor field. Okay, mu nu. And G mu nu is symmetric matrix with positive eigenvalue. B mu nu is an unsymmetric matrix. We can repeat this exercise. Del S is equal to 0, and then impose a condition that the equation of motion, which is del A G mu nu del A x nu is equal to 0. So this is a bulk equation of motion. So you impose this bulk equation of motion, then the variation of the action, then the variation of the action gives you a boundary integral of dza 4 pi alpha prime, the boundary integral epsilon ab. And so what you have is, so from here you get G mu nu. Okay, so let me write it this way. So there, let me write it over here. Del x mu G mu nu del B x nu plus G B mu nu. So del B x nu. Excuse me. Yeah, so this is actually unsymmetrized epsilon AB. Yeah, so this was important. Yes, please excuse me. So yeah, so I didn't write the action correctly. So I apologize. So you have this, and then this is a hazard of treating indices. Not carefully. So I should have had the epsilon tensor over here. Because this is unsymmetric, so if this is del A, then this would vanish because this would be symmetric, right? So you have to contract this by epsilon AB. So this was important. So I forgot to mention that. So I apologize. So then you have this. So this is this times GAB del X. Sorry. What am I writing? G mu nu del B x nu plus B mu nu epsilon BC del C of x nu. Okay, so this is a little bit complicated, but let me, please bear with me for a moment. So this epsilon contracted with this epsilon just gives you Kronecker delta. So that means that, so if we have, so with G mu nu and B mu nu, so what I wanted to say was that the boundary condition is either del is equal to 0, and this is still Dirichlet. But Neumann condition is slightly different because now this derivative is in the direction perpendicular to the boundary, but this derivative is in the direction parallel to the boundary because this direction are orthogonal to each other on the world sheet of string. So we could write this as G mu nu del perp of x nu plus B mu nu of del parallel of x nu is equal to 0. Okay? So parallel means that you are taking derivative along the world sheet, along the boundary. So this is perpendicular to the boundary, this is parallel to the boundary. Okay? So you can think of this as a mixed Neumann and Dirichlet condition. Because this being equal to 0 is a Neumann condition, but you can think of this being 0 as Dirichlet condition. Because if you have Dirichlet condition, then the value of x on the boundary is the same. So therefore, if you take derivative along the boundary, it should vanish. So you can think of this as a mix of Dirichlet and boundary, Neumann boundary condition. So you see that if you turn on the B field, then in general the boundary condition is either Dirichlet or mixed boundary condition. So there is some subtlety associated with that. There is one more thing we can do. Which is related to what I wanted to say next, which is the following. So I said that the action is of this form. But there is one more thing to do, what we can do, which is to add a term on the boundary. So if you have a boundary, you also have a possibility of adding some gauge field on the boundary. You can think that there is some kind of gauge field living on the boundary, and you can. So there a x mu, okay. So then you can actually add this to the boundary, okay. And this comes from the following thing, that if you have D-branes ending in this direction, then you can have open string like that. So just like if you look at the spectrum of closed string, so type 2A or 2B in the bulk, and study the spectrum, the massless sector are the supergravity. And these have n equal 2 supersymmetry in 10 dimensions. So you have n equal 2 supergravity. So n equal 2 supergravity has 32 real supercharges. And as we have seen, the type 2A and type 2B string theory in the bulk has a low energy effective theory where the massless sectors are graviton, dilaton, and B field, and a bunch of antisymmetric tensor field coming from Ramon sector, plus their n equal to supergravity partners. Open string also has a massless sector, and but they have less supersymmetry because boundary condition like this breaks half of the supersymmetry. So you have 16 supersymmetry, and give rise to n equal 1 super-Yang-Mills. So it is a Yang-Mills theory. It's not a gravitational theory because the open string massless sector does not contain graviton. Gravitons are in the massless sector of closed string. So you have n equal 1 super-Yang-Mills. So in 10 dimension, n equal 1 super-Yang-Mills consists of gauge field. If your D-branes not stretched over space-time, but in the subspace of that, it will be a reduction of super-Yang-Mills, so it contains also some number of scalar field. So anyway, you have this kind of supersymmetric Yang-Mills theory on the world volume, and this gauge field A mu corresponds to that gauge field. So you have a possibility of adding this to the boundary. You can also have a possibility of adding scalar field to the direction normal to that, but let me avoid that additional complication for now. Let's just pay attention to the possibility that if you have a boundary, you can actually add gauge field as motivated by this consideration. So then we repeat this exercise. We will repeat this exercise again, which is to say that you require the condition that del S is equal to 0. And you ask, well, what kind of boundary condition that it should satisfy? Okay, so we do the same thing again. So what's going to happen is that we have to take variation of the boundary term also. So if we take variation of this, then this is going to give you del nu of A mu of x del A x mu, right? So this is one term coming from the variation, if you take a variation. But you also have to take variation with respect to this, and then you have to take total derivative, commute that. So that's going to give you a commutator of this, and that is a field strength. Okay, so now this mixes with this. So therefore, this is going to give rise to the equation that the G del mu nu del T this plus B mu nu plus F mu nu del parallel of x nu is equal to 0. So if you have a Maxwell field on the D-brane, actually the B field in the bulk and B field or the field strength on the boundary mixes under a gauge field configuration. Okay. You can ask, well, what happens if you add scalar field? In general, this massless sector also have massless scalar field. That's going to modify the Dirichlet condition in that case. Because if the scalar field has non-zero value, effectively what's going to happen is that now the D-brane starts fluctuating. The D-brane configuration is not straight, but it can actually be curved. And that modifies the Dirichlet condition. So adding scalar field on the boundary, scalar term on the boundary actually modifies the Dirichlet condition. Here I'm pointing out that if you add gauge field, if you turn on the gauge field on the boundary, this Neumann boundary condition is modified in this way. Okay? So it's interesting that the B field and F field mixes with each other. And so this phenomena has a lot of interesting consequences. So let me actually, let me just give you the condition in the full glory. So the condition that then give you is that if you start with action, which is G mu nu del x mu del A x nu plus B mu nu del A x mu del B x nu epsilon AB plus the boundary term A mu x D x mu, then the boundary condition on this is either del x mu is equal to 0 or g mu nu del half x nu plus b mu nu plus f mu nu del half x nu is equal to 0. So if you have just one D-brane, and so therefore if the Maxwell field is abelian, then there is a mixing of B field and F field on the D-brane. So this is interesting. So you can ask what the gauge symmetry is. So gauge symmetry, remember that there are two gauge symmetries. One is that the A mu can transform with the derivative. So this is a standard gauge transformation. But B field can also change by del mu beta nu minus del nu beta mu. But if you look at this, then you see that on the boundary, the natural combination is B mu nu plus F mu nu. Okay, so how does this transform? Well, this is going to transform into B mu nu plus del mu beta nu minus del mu beta mu plus F mu nu. So it's funny because this is not gauge invariant anymore. But you'd like this kind of physical boundary condition for D-brane to be gauge invariant. But there's a way to remedy that, which is to say that if you actually, when you do the B field, gauge field transformation B field, you're going to shift A. So that this can be observed into F. So maybe I put minus sign so that they cancel. So that this is invariant. So if you do this, if you require that under the gauge transformation of the B field in the bulk, the gauge field on the boundary, on the D-brane, has this inhomogeneous shift, then this is gauge invariant. Okay? So somehow the consistency of the D-brane boundary condition requires this type of inhomogeneous gauge transformation of the A field. This is actually related to the Green-Schwarz mechanism also, but for the B field, but that's beyond the scope of this discussion. But anyway, so I just wanted to point out that there is this kind of generalization. Okay, so let me get back to the discussion of D-brane. So this is the D-brane boundary condition of the boson. So let me just consider, so this was for general configuration of the massless field, the metric and B field, etc. But suppose, for example, we just have a flat Minkowski space. So G mu nu is eta mu nu, and B mu nu is 0 for now, and the gauge field is trivial. So let's consider this type of situation. Okay, so in that case, let's choose the coordinate specifically for simplicity. So let's choose a coordinate on this. So let's suppose the worldsheet is like cylinder. and then the worksheet ends. So suppose you have a D-branes like that, and then suppose there is a string coming in and end on it. Okay. So to do the calculation precisely, let's try to specify the coordinate. So the string comes in this way. Okay, or goes out in this way, whichever you like. Maybe it's better to draw it this way. So let's draw it this way. Excuse me. So suppose we have a D-branes, and then suppose a string ends here and then come out in this direction. Okay. So maybe I should use dotted line. But then so there is a sigma naught direction which goes from 0 to infinity. Okay, so this is infinity, and this corresponds to C naught is equal to 0. Okay, and excuse me, no. Let's see. So please excuse me. I think I didn't specify. So let me see. No, I think the configuration. So let me see. Oh yeah. So please excuse me. So So let's consider the following parameterization of the worksheet. So let's consider upper half plane. So this is a Z plane, and then this corresponds to the imaginary part of Z is non-negative, and so this corresponds to the boundary where our imaginary part of Z is equal to Z. Okay. So and then what I should have said, please excuse me, is that I'm going to parameterize this Z to be e to the xc naught plus I xc1, and I restrict the xc1 to be between 0 to pi, so that so if this is origin, then the xc1 goes in this direction. So basically sweep out the upper half plane. Okay, and okay, so in this parameterization, you have a choice of either del x mu is equal to del bar x mu, or del x mu is equal to minus del bar of x mu, depending on whether you impose Neumann boundary condition or Dirichlet boundary condition. Okay, this is what I should have said. Now, if you have a superstring, we should also worry about the boundary condition for fermions. And the boundary condition for fermions is imposed by requiring consistency of the worldsheet superconformal symmetry. So there is a superconformal generator. If you remember our discussion in the first quarter, we have super current on the worldsheet, which takes the following form. So this is for the left mover, and the right mover has this super current. Okay, so you would like the boundary condition to respect to at least half of this worldsheet supersymmetry, so that the string propagation can happen consistently, and we can remove negative norm state, etc. So that would require G left to be called either plus or minus G right on the boundary. Okay. The reason that we allow plus and minus is that when we have we identify left moving supersymmetry and right moving supersymmetry, we need to do that in order to respect the supersymmetry algebra. And so that means that gluing should be done by up to the automorphism of the algebra. So you can ask, what is the automorphism of the supersymmetry algebra? Well, one of the important thing is that if you have supersymmetry, Q squared is equal to H. So, well, you want to preserve Hamiltonian, but if you have this algebra, there is actually a Z2 automorphism of the algebra, which changes Q to minus Q. Because if you flip the sign of Q, this algebra is preserved. So there's actually an automorphism of supersymmetry algebra, which allows you to multiply plus or minus sign to the supersymmetry. So this is related to this choice that you made. So if you have this boundary condition, this gets mapped to here. So that means that you can have psi left identified with the psi right up to sign. Okay. Now, if you choose minus sign, if you choose this direction, then you have the same ambiguity, but then it should be flipped. So that means that the boundary condition for fermion will also have sign choice, but the sign choice is correlated, inversely correlated to the sign choice we make over here. So anyway, so these are the supersymmetry dictate what kind of boundary condition we should choose for the fermion. Okay? So once we have this kind of boundary condition, then we can do various useful calculation. So one thing we may consider doing is to calculate the force between D-branes. And the reason that this is interesting is the following. So remember that we are expecting this D-brane to be an object which carries Ramon-Ramon charge. But it also has a tension. That it has a mass per unit area of D-brane. So suppose you have two of them with the same D-brane charges, same Ramon-Ramon charges. Then we would expect them to interact with each other. You can calculate force between them. So if you have D-branes, so what I mean by force between D-branes? Well, so it's going to emanate. So it's charged with respect to the P-form gauge field. So that means that it can emanate this gauge field, and they interact with each other. They are the same charge. They have the same charge, the same sign. So that means that they try to repel each other, just like if you have Maxwell field, and if they have the same charge electrons, then they repel each other. So there is a force that sort of try to repel each other. But there is also a gravitational force. And so if you have a p-dimensional extension of, so this is time. If you have a p-dimensional extension of the work volume, then there is a mass per unit volume in this direction, and they try to attract with each other. Okay, so there is a force between them. So how do you calculate them? Well, so all of these are in the massless sector of a closed string. So namely that each one of them is actually closed string. So all these can be calculated by just considering the following diagram. So if you consider two D-branes and consider the process, the two D-brane exchanges all possible closed string emanated from one side and absorbed to the other side, then this includes this. But there may be other ways that the two D-brane can exchange forces. For example, in addition to gravitons and unsymmetric tensor field, this can emanate all sorts of massive closed strings. And they can also be exchanged with each other and generate forces. This single diagram includes all of this. So we just need to calculate this diagram to calculate the force. And what you do is the following. So suppose they are separated by the distance r. Okay? And then you want to calculate the energy for this configuration as a function of r. That should calculate for you the potential energy for placing this D-brane with distance r apart. So we can calculate this. And this calculation is not that difficult because what you do, the thing you do is to consider this diagram. So you want to calculate the diagram where closed string is emitted and absorbed, right? This seems like a hard calculation to do, but if you change perspective, it's not that difficult. And the reason for this is that instead of considering this diagram as a closed string is emanated from one side and absorbed by the other, this diagram is actually equivalent to the calculation where you have open string going in this direction. So you can think of this as open string one loop diagram, where open string goes around and come back and then we calculate this. And this we know how to do the calculation, because the one loop energy generated by this open string is just an integral of open string. So open string can move along these D-branes and carries momentum. So we have to integrate this open string momentum. And open string can, end point of the open string can move around on the volume of D-branes. So open string can have k-dimensional momentum. So k mu is open string momentum. And then you have to just sum over open string physical state with mass n, and then you calculate e to the minus. And then depending on you have fermions, a boson, you have opposite sign. So I can write this as minus 1 to the f. This f is a space-time fermion number. So if you have gauge field or scalar field, f is 0. If you have fermion partner, you have minus 1, etc. And the e to the minus pi t k square plus m square divided by 2 with appropriate normalization. And the t is a Feynman parameter. T is a Feynman parameter, so this epsilon r is equal to minus of integral dt over t, 0 to t. So t is a standard Feynman parameter that you use to run this calculation. So this is just this calculation. Okay, so this yes, okay.
So for the closed string picture, this integration can be seen as integration of the moduli space of the.
So both are integral of a moduli space of the sphere with two holes.
Okay.
Right. So you have if you have annulus, if your worldsheet is annulus, like that, there is only one real moduli on the worldsheet. which is either, you can think of this as a distance between them. And this t is a Feynman parameter. Actually, in this case, actually, this t is this direction. Yeah. So anyway, so you have this open string. So you can think of this as either cross string exchange, the open string exchange. But in either case, the diagram we are calculating is a sphere with two holes or annulus, the same thing.
So
And yes.
my question is, I understand the measure. Can you remind me how the t appears in the exponent inside the
Beg your pardon?
How does the t, the moduli?
Well, because the moduli is a rate. So if you think of one way to define the moduli is that if you have a cylinder with a finite length, you can normalize this direction to be pi, and you can parameterize this direction by t.
I see.
And this is so therefore the t coupled to the Hamiltonian on the wall sheet, and the Hamiltonian on the wall sheet of the so basically you can write this as a super trace or trace -1 to the f e to the minus t times L0 plus L0 bar, where this is a Virasoro generator, and this is Hamiltonian, and the eigenvalue of L0 plus L0 bar in this open string sector is a momentum square plus mass square divided by 2. So it's this one, and maybe there's a pi here.
And do we care about higher genus corrections to the closed?
Yeah, you do care, but so I will tell you they all vanishes in this setup.
Because
So.
it's half EPS, right?
Yeah. So what I want to demonstrate is the one loop diagram vanishes, but the higher loop also vanishes for similar reasons. So the point I want to make, however, is that this can be calculated exactly. Okay, so this is ER. So I just write it more formally, like d dt over t 0 to infinity of a trace of -1 to the f e to the minus pi t of L0 plus L0 bar in the open string. Okay, so this is the calculation we do, and then this is just the open strings are just bunch of harmonic oscillator for x and size satisfying these boundary conditions. So we can repeat this exercise and calculate this. And so if you remember our calculation in closed string one loop diagram from the last quarter, their results are expressed in terms of theta functions. So the answer can be expressed as -2. It can be expressed as the integral of dt over t 2 pi square t minus 1/2 of p plus 1. So this factor depending on. So the reason that this factor depending on p is that you have an integral over momentum, and each integral momentum gives rise to 1 over square root of t, right? Because this here is a Gaussian integral. Here's a Gauss integral over k. So each direction gives you 1 over square root of t, which is this one. And then you have e to the minus 2 pi r square over t. And the reason you have r square over here is that you have mass square here. And we are calculating the mass spectrum of open string going between here. But this open string is stretched with distance r. So if you stretch the string in distance r, because strings has tension, so this ground state of open string has a mass already. And that mass is given by r, proportional to r. So this gives rise to r squared times c. So this is a contribution of the mass. And then there is some additional piece which depends on t, and that can be calculated by summing over spectra. So that is equal to -1/2 of s is equal to 2, 3, 4, -1 to the s, the theta function. Okay. So this is a very standard calculation. You know the excitation of bosons and fermions, and from that you can calculate this. And the reason that you have eta to the 12 is 1 over eta to the 8 coming from the excitation of bosons in the right quantum direction in 10 dimension, and additional eta to the 4 coming from fermions. And fermion gives you half of the contribution of the boson, so you have 1 over eta to the 4th, and adding them gives you eta to the 12 in the numerator. And then, depending on the spin structure, you have different theta functions. So there's the theta 2, theta 3, theta 4, 3 types of theta function contributing to this. And the reason you have sign is that you can have Neveu-Schwarz sector and Raman sector in open string. So Neveu-Schwarz sector contribute with the positive sign, Raman sector contribute with negative sign. Okay, so this is the final answer. So let me again explain. So this is just a simple open string one loop diagram. You just sum over all the physical state of open string going between these two D-branes, and this power comes from integral over momentum of the open string state. This shift by r squared over 2 pi comes from the fact that if you stretch open string at distance r, which is the separation of the two D-branes, the mass, the ground state mass is proportional to r, and then excitation gives rise to this. Okay, so this is an answer, but there is actually a further simplification, which is to say that this is equal to 0. And that comes from this theta function identity that we already used in the last quarter. This is the Jacobi's identity. You can actually, if you like, you can expand the theta function in power and check it, but this vanishes. And so therefore there is no force between these two D-branes. So this can be seen, this is sort of a full string test of the statement that, so for example, graviton exchange and gauge field exchange cancel with each other in terms of the attractive force by graviton is cancelled by repulsive force of gauge field, and this happens for all the massive or cross-string exchange also. So this confirms that for this configuration there is no force between them. But you might feel like well, this is sort of waste of resource of calculation, because you do this all hard calculation of the theta function, and the final result is 0. So you want to do a little bit more. So you want to actually do some little useful calculation. So you can actually do a little useful calculation, which is to say that so this is 0, but we can actually this equation this calculation contains more information than just saying it is 0, because each term in this summation has some information. So you can actually by going through this calculation, you can actually isolate the contribution from graviton and contribution from a gauge field, and the reason is the following. So remember that so the parameterization was such that that t goes in this direction. T goes in this direction, and so that means that T large corresponds to the case where you have open string, you have a light open string exchanged. So because when T is large, this cylinder is, the radius of the cylinder becomes long, so this direction becomes long. So if you have a highly excited open string, it costs you energy, so they're going to be exponentially suppressed. So for T is large, the state propagating around here is a light open string. But on the other hand, suppose T is small. So when T is small, what's going to happen? is that you have a very, very long cylinder. So T is long. T is going to become long. So namely that the ratio, so this is this direction. So if this is small, relatively this is large. So you have a very long cylinder. So that means that when T is small, we have a light closed string contribute dominantly to this amplitude. So in particular, in the limit when T goes to small, then you should be able to isolate the exchange of graviton and unsymmetric tensor field from this calculation. And you can see that this Z of T that I have written over there can be written as, so there are two positive contributions and one negative contribution, and you can see this is actually equal to 8 minus 8 times T over 2 to the 4 plus order 1 of e to the minus T 1 over T. So you can think of this as a massless cross string exchange. And then these are exchange of massive cross string. Okay, and you can think of this 8 coming from the exchange of graviton because it gives you attractive force, and this 8 comes from the exchange of massless unsymmetric tensor field. And if you actually do this calculation carefully with normalization, then you can actually reproduce this equation that the mass is equal to n over 2 pi to the p g string n string to the p plus 1. So remember that this was the formula that we derived for the extremality condition for the black D-brane. And here we are considering just one D-brane, so n is equal to 1. So from this, you can actually infer the value of tension of the D-brane, the mass per unit volume, and exact normalization of this, and it actually reproduces this formula. Yes, please.
Is this by matching this expression with the graviton exchange?
Yeah. So that's correct. Yeah. So you can do the calculation. You can do the suppose you have a mass of D-brane or tension of D-brane. You can calculate the graviton exchange, the potential generated by graviton exchange, and the potential generated by gauge field exchange, and you can compare that with this, and from that you can infer the charge and mass of the D-brane, and this matches with this calculation. So this was a very important calculation. This confirmed that the D-brane indeed carries the mass and charge corresponding to what's expected for the P-brane in type 2 string set. So this important calculation was done by Joe Polchinski and his famous paper in 1995 called Dirichlet brane and Ramon charges. And here this Ramon charge is the title of the book, the paper, because one of the points of the paper was to actually reproduce this formula from this open string calculation. So Joe was an undergraduate student here at Caltech, and some time ago I had some conversation with Polchinski, and so he told me the story of how he actually checked this calculation. So so in 1995 was a rather exciting year because we then proposed this duality program at the string conference at USC, and so everybody started working on this, and Polchinski was interested in revisiting the idea of D-brane that he proposed many years ago. But he was invited to a conference in Kyoto in summer, and he didn't want to go because he rather stayed at home and do the work rather than traveling all the way to Japan. But he's an honorable person, so since he agreed to go to the conference earlier, so he actually went there. But he was doing this calculation, and then he told me that he completed this calculation while he was doing laundry in the laundromat. So there was a laundry, and then he was using Notepad to do the calculation, waiting for his laundry to be completed. And then he actually did this calculation. So he said something positive came out from trip to Japan. So anyway, so this was a very important calculation. This confirmed that the D-branes and D-branes are the same thing. So now, given this, we can try to see whether some of the property we expect for D-branes and object charged with respect to the Raman gauge field are reproduced as a property of D-branes, and whether we can learn more about these objects from the D-brane description. So let me try to do that. And the first thing I wanted to discuss was the property of D-brane and the T-duality. So remember that the T-duality is also something that we discussed in the last quarter, which is a property of cross-string theory propagating on torus. And there was some unexpected behavior. So the simplest example was the following. So suppose you have a 10-dimensional string theory, but then consider compact by one of the dimensions to be a circle of radius r. Okay? So you have a circle of radius r. And one of the curious property is that the cross-string propagating on a circle radius r is the same as the cross-string propagating on the circle radius 1 or 2 of r. So large radius is the same as small radius, but that is given but that requires identifying the exchanging the mass, so it's exchanging the momentum and winding number of string in the following sense. So let's choose a coordinate in this direction to be 0, 1 to 8, and coordinate in this direction to be x9. So x9 is identified with x9 plus 2 pi r, because the coordinate x9 is supposed to be living on the circle of radius r. And so del of x9 is given by 1/2 of momentum divided by r plus maybe square root of 2 plus winding number times r plus oscillator, and then del bar of x9. My handwriting is so bad, so it's kind of hard to distinguish 9 and 8, so this is meant to be 9. 1 over square root of 2 m over r minus w over r plus oscillator. And this oscillator piece is independent of r. So as far as the string oscillation is concerned, the only thing that depends on r are momentum and winding number. And the momentum is quantized by 1 over r. So this is Heisenberg uncertainty principle, that if you have particle moving on the circle radius r, then the momentum is quantized in the unit of 1 over r. And but if you have a string can also wind around the circle. And if you go around once, then the mass of the string gets increased by the factor proportional to 2 pi r. And so this gives rise to these contributions. Okay? And but if you look at and then from this you can calculate the spectrum of the string. For example, the energy momentum tensor is 1/2 of del x squared. So from this you see that there is a contribution to the energy momentum tensor of something like m over r plus w r square, and then t bar is equal to 1/2 of del bar x square, which is like a quarter of mr minus wr square. But you see that we can actually exchange r to 1 over r or 2 or 1 over r. I guess in this normalization, 1 over r. So let's see. I think I didn't do the normalization correctly. So I think we should have half, and we should have 2. So this is 1/8. It's not very important, just matter of convention. I think 2 over. And exchange of m and w. If you do this exchange, then these two are exchanged. Sorry, these two are invariant. Okay, and but actually, to be precise, the oscillator has to change sign, because if you do this exchange, you get the right mover. The sign of the right mover changes, so that means that the left mover is not modified, but the right mover oscillator should change the sign. Okay, so this is something we should remember. So this means that so initially, so this is for cross string. Okay, so for cross string, the T-duality for circle compactification means that we exchange momentum and winding number, and also exchanging the oscillator to be the same for the left mover, but changes the sign for the right mover.
Does it change the sign of the operator or the label?
It changes the sign of del bar of x, but not del of x. Okay?
And then alpha over there is the operator for the oscillator.
Yeah. So this, I wrote oscillator here. So to be precise, what I meant is summation of alpha right m e to the minus mz or something. So these are oscillators. Okay, so then you can ask, well, what happened to D-branes? So you can ask what happens if you do the T-duality with D-branes. So the effect of T-duality, as we just saw, was that under T-duality, del x 9 goes to del x9, but del bar of x9 changes the sign. Okay, so one of the effects of this is that this switches, this exchanges. If string theory has a boundary, then it exchanges the Dirichlet and Neumann boundary condition. So suppose you have a boundary of the string. On the worksheet, you can have a Dirichlet boundary. You can have a Neumann boundary condition. And you can have a Dirichlet condition. I wrote Dirichlet condition as del x mu is equal to 0, but this is the same as derivative of this x parallel to the D-branes, parallel to the boundary. So this is the direction parallel to the boundary, and this is the direction perpendicular to the boundary. So if the value of x is the same on the boundary, it means that derivative parallel to the direction itself. You see that if you do this T-duality transformation, in the direction of T-duality, you are doing T-duality, these are exchanged. By T-duality. Because so if you choose, for example, the coordinate so that this is the boundary. So suppose I choose a parameterization just like we did here, that a boundary is the real axis, and then the worksheet is a positive real axis, real imaginary positive part. Then the Neumann correspond to del minus del bar of x is equal to 0, and the Dirichlet correspond to del plus del bar is equal to 0, right? Because derivative del plus del bar is a derivative along the boundary, whereas del minus del bar is a derivative perpendicular to the boundary. But you see that if you do this, then these are exchanged. So that means that under T-duality, the Dirichlet direction and Neumann direction on the boundary is exchanged. So what does it mean? So what it means is that the dimensionality of D-branes get modified. So suppose you have P-branes, dP-branes. And there are two possibilities when we consider T-duality. So suppose you have D-branes, and suppose you have some kind of target space, which is like circle. So for example, suppose this is S1 direction, and suppose this is 1, 8 direction in that picture. So there are two possibilities. So suppose D-branes extended in this direction. Suppose you have dP brane extended in subspace in 9 dimension, but is localized in the circle direction. Then under T-duality, so this is the radius of. Under T-duality, it wraps, it's extended now to the cylinder direction also. So it becomes dP plus 1 brane. But now the radius is 2 over r. I'm using 2 over r because I'm using the unit where alpha prime is 2. On the other hand, if the D-brane is wrapping on in the direction of the circle, where we are going to do the T-duality, then under T-duality, under T-duality, 2 over r, it gets localized in this direction because Dirichlet direction and Neumann directions are exchanged. So it becomes dP minus 1 brane. So that means that if the D-brane is wrapped in some particular direction, and if you do that T-duality in that one dimension, the dimension of the D-brane either increase or decrease by 1 depending on whether D-brane wraps in that direction or not wrapping in that direction. Yes?
Question, is there a description of this in terms of the supergravity?
Yes, that's where I'm coming to. So now remember that if you have type 2A string, it had, so what it had? So it had 1 form gauge field, 3 form gauge field, and 5 form gauge field. Etc. So odd form gauge field, and field strengths are even form. Type 2B string had even. Well, and in particular, this gauge, 4-form gauge potential is self-dual in the sense that its field strength 5-form is self-dual. Now we know that under T-duality, type 2A and type 2B are exchanged. So that means that we would expect that these Ramon-Ramon tensors get exchanged to each other from odd rank to even rank, etc. Now, for each one of them, D-brane carries charges. So, in type 2A, you have odd rank tensor. So that means that type 2A string have dp branes with p is equal to 0, 2, 4, 6, etc. Because if you have t spatially extended object, you have one more time, so you have p plus 1 dimensional world volume of dp branes, which can couple to odd rank tensor. If you have type 2A to type 2B string, you have dp branes with p even. So you can have, well, in principle you can have -1, which couple to this one, and then 1, 3, 5, etc. Okay? So you see that this is odd, this is even. So under T-duality on the circle, these get exchanged, and indeed these get exchanged. What we saw was that if you have, say, D2 branes in type 2A, and if this D2 brane is wrapping on the circle, and if you do T-duality, then it becomes D1 brane, and that's in 2B theory. So that's consistent. Whereas if this D2 brane is not wrapping on a circle, and if you do T-duality, it becomes 3 branes, and it's right here, over here. So therefore, the way that D branes transforms into each other, and the way that type 2A string and type 2B string get exchanged under T-dualities are consistent with each other. Okay? In the next lecture, which is going to be on this Friday, I will tell you a little bit more about D-branes and also its properties on Calabi-Yau manifold. So far we consider D-branes in flat space, but it's fun to consider more general curved space and think what D-brane would do in general curved space. So we'll discuss briefly that. And if we have time, we'll go on to discuss the ADS application to ADS shift correspondence. So we'll meet again. So we'll have extra lecture on this Friday at 9 o'clock at the same place.